Year 13, Chapter 10, Integration, Lesson 8, Integration by Parts. So I want you to start off by looking at these two examples here. Now in these integrals, we can't integrate them directly by inspection, and we can't use integration by substitution. You can try, but what you'll find is that you won't get very far. So for instance here, well, if I say let u equal x, then all that happens is this integral x e to the x, which is in terms of x, becomes the integral of u e to the u du. So it doesn't change in complexity, and we still can't integrate it. Let's try this second one here. Now, if we let u equal sine x, then as soon as you start differentiating, you can see that you're going to get a result which isn't going to have any neat cancellation, and you'll end up with, most likely, an even more complex integral than the one you started with, a mixture of x and u, and we can't easily replace the variable x in terms of u. So integration by substitution, unfortunately, in both these cases, is simply not going to work. So we need a different method to integrate both of these integrals. So we are going to derive a formula which allows us to carry out something we call integration by parts. Now, we start off by thinking about differentiation. And in particular, we start off by thinking about the product rule, which tells us that the derivative of a product, uv, where u and v are functions of x, is equal to u multiplied by dv by dx plus v multiplied by du by dx. Now, here's what we're going to do next. We're going to integrate both sides of this with respect to x. So I can write that out in the following way. I've got the integral of d by dx of uv with respect to x is equal to the integral of u dv by dx with respect to x plus the integral of v du by dx with respect to x. Now, let's look at the component parts of this. On the left-hand side here, we have a derivative with respect to x, which is then being integrated with respect to x. So think about what's going on here. We have uv, which is being differentiated to get d by dx of uv, and we're then integrating it, which would take us back to uv. So on the left-hand side, we can actually evaluate this integral, and it basically takes us back to the result uv. On the right-hand side, everything has to stay as it is, and we have the integral of u dv by dx with respect to x plus the integral of v multiplied by du by dx with respect to x. And we actually rearrange it so that we isolate this part here. So this then gives me the result the integral of u multiplied by dv by dx with respect to x is equal to u v, the product of u and v, minus the integral of v multiplied by du by dx with respect to x. And this is the law we use to carry out integration by parts. So let's have a look at a few examples. So I'm going to go back to the example, the integral of x e to the x dx, which we looked at earlier on. Now, the key thing that you must notice is that we are looking at a product. And integration by parts is all about integrating products of functions, which we cannot do using the simpler integration by substitution process. So let's look at the law here. Now, look at the left-hand side. Can you see that there is a product here? So we go back to our integral, the integral of x e to the x, and one part of this has to be u, and the other part of this has to be dv by dx. But we have to think to ourselves, what happens to u? Well, u ends up here, nothing happens to it there, but it also ends up here, which means u has to be something that we can differentiate fairly easily and which isn't going to become something more complex usually. Now, what happens to dv by dx? Well, it turns into v here and here, which means it's been integrated. So dv by dx, the part that becomes dv by dx, has to be something that can be integrated very easily. Now, choosing the two parts is something that requires practice and familiarity, and it might be difficult to see which is which to begin with, which is why you have to see lots of examples and try lots of examples to really get the hang of this process. You may do it wrong to begin with, which is absolutely fine, and you will notice that it quickly turns into something you can't integrate if you go wrong in your choice. And we will have a look at what happens if you go wrong in your choice in a minute. Now, I'm going to choose for x to be u, and I'm going to choose for e to the x to be dv by dx. So, u equals x, remember, u gets differentiated, so du by dx is equal to 1. And I'm going to choose dv by dx to be e to the x. And remember, dv by dx has to be integrated, so e to the x integrates to e to the x. Now, there is no need to include a plus c at this stage. You can do that at the end. Okay, there's no point putting in a plus c here, which is just going to complicate your work unnecessarily when you can just do that at the very end of the process. So let's make ourselves some space and let's have a look at the integral. So we are carrying out the integral of x e to the x with respect to x. I'm colour matching this so you can see how the different parts match up. Now, the first part is u multiplied by v, so that's these two multiplied together. So that's x multiplied by e to the x. And then following the formula, we need to subtract from that the integral of v multiplied by du by dx. So that's this multiplied by this. So that's e to the x multiplied by 1. Seems silly to write multiplied by 1, but I'm just doing that to demonstrate the whole process. So this then gives me x e to the x minus, now here I've then got to evaluate the integral of e to the x. The multiply by 1 doesn't really make any difference, and of course that gives me e to the x, and then I have plus c at the end. So you can see how the process has worked really nicely. Now, it's really important that whatever you choose here has got to result in a simpler integral. So if you end up with a more complex integral than when you started, you know that you have chosen incorrectly in the first place. So let's discuss for a moment what might happen if we choose u and dv by dx incorrectly. Let's go back to the integral that we've been working on, the integral of x e to the x dx. And this time, what I will do is I will choose u to be e to the x and dv by dx to be x. So that means e to the x is differentiated, which just gives us e to the x. And then remember, I've chosen dv by dx to be x, and that has to be integrated to give me v, so that gives me a half x squared. Now, you should already start to see this as a bit of a warning here, because v is now more complicated than in the original integral. So we've ended up with something a little bit more complex. So let's have a look at our integral. We've got the formula set up here. So we want the integral of u dv by dx, so that's e to the x and x as a product with respect to x. And this is now equal to uv, so that's these two multiplied together. So that's e to the x multiplied by a half x squared. And we need to subtract from that the integral of v, a half x squared, multiplied by du by dx, which is e to the x, with respect to x. Now, look at the problem we have immediately hit. This integral here is more complex than the original integral, which is actually a lot simpler over here. So integration by parts has failed here because we chose u and dv by dx the wrong way round. And ultimately, whatever you are integrating needs to result in something here that is going to be simpler for you to then integrate. So it becomes very apparent very quickly when you have chosen incorrectly. So let's look at our second example here, which we've seen previously. Note the product of x and sine x. Now I'm going to choose u to equal x, which differentiates very quickly to give me 1. And I'm going to choose dv by dx to equal sine x, because of course when we integrate sine x we get negative cos x, so it's not really becoming any more complex, it's staying at its sort of same level of complexity. Now, the formula we need is up in the top right hand corner, so let's work it through. So the first part we have is this part here, which is u multiplied by v. So that's x multiplied by negative cos x. And then we're subtracting from that the integral of v, which is negative cos x, multiplied by du by dx, which is just 1, all with respect to x. So simplifying this, we get negative x cos x minus, notice that here, so this simply becomes plus the integral of cos x dx. And what does cos x integrate to? Integrates to sine x, and then let's include plus c at the end. So what was noticeable here was just how much simpler this integral became when we used integration by parts. And that's because we chose correctly here when we chose our u value and our dv by dx functions. Now, this next example is really interesting. You can see the product straight away, x ln x, and there will be some temptation perhaps to use ln x as the dv by dx, the part that you integrate. But at the moment we don't know how to integrate ln x. We can differentiate it, however, so this has got to be u, the part that gets differentiated, and x has got to be dv by dx, the part that gets integrated. We've got no other choice because at the moment we don't know how to integrate ln of x. So this is going to be really interesting to see how this pans out. So u equals ln x, differentiating ln x, we know we get 1 over x, and dv by dx, we know, is then x, which integrates to give us a half x squared. And we might be worried that this looks a little bit more complex, but actually, as you'll see in a second when we do the integration, we have nothing to worry about. So let's apply the laws of integration by parts here. So we want to start off with this part here, so u multiplied by v. So that is ln of x multiplied by a half x squared, and we're subtracting from that the integral of v, which is here, multiplied by du by dx, which is here. So have a look at what's going to happen in a second. We have a half x squared multiplied by 1 over x. So the first part of this I would neaten up and write as a half x squared ln x to ensure we have full clarity. Now the second part of this, the half can come outside the integral sign as we've seen previously, and then all that happens is x squared and 1 over x simplify very nicely to give us the integral of x. So a really easy integral, and we end up with a half x squared ln x subtract a quarter x squared plus c. So it becomes a really easy integral because of this cancellation here. Now you'll find that's a common result when you're integrating by parts involving an ln x function. The ln x function will usually be the u function which is differentiated because we don't know how to integrate it yet. And as we find out how to integrate it, you will see that it integrates to something quite complex. So this next integral is really interesting because you might look at it to begin with and wonder, well, where is the actual product? But what we can always do is write this as 1 multiplied by ln of x. Now, as we said previously, when an integral which we're trying to integrate using integration by parts involves an ln function, we want to differentiate it rather than integrate it. So ln of x is going to be our u part, and 1 is going to be our dv by dx part. So u equals ln x, which gives me du by dx is equal to 1 over x, differentiating, and then dv by dx is going to equal 1, which we can integrate to give us v equals x. So let's take a look at the formula. So remember, we first of all want the product of u and v, so that's ln x multiplied by x. I'm using a bracket here just for clarity. Subtract from that the integral of v, which is x, multiplied by du by dx, which is 1 over x. And again, you see that very neat cancellation is going to take place, giving me with x ln x minus the integral of 1 with respect to x, and 1, of course, integrates to give me x. Now, I haven't used the modulus in any of this, so really we're assuming that x is greater than 0, otherwise we need to make sure we include a modulus function here and here. Now, that is actually a very useful result to memorise. You should learn the process by which we integrate ln of x, and you should also learn that the integral of ln of x with respect to x is x ln x minus x plus a constant. So let's have a look at a definite integral. Now the first thing I'm going to do is rewrite this as the integral of x e to the negative x dx. Now, similarly to last time, I want x to be u, and I want e to the negative x to be dv by dx, because essentially it doesn't integrate to something that is more complex. It integrates to essentially itself. So let's set everything up. U is equal to x, which gives me du by dx is equal to 1. And then dv by dx is equal to e to the negative x, which gives me v equals negative e to the negative x. Now, let's write down the integration by parts formula. Now, let's start off here with uv. So I'm on this part here. So that's x multiplied by negative e to the negative x. We'll put in a big square brackets, and of course the limits 0 and 4 will need to be substituted into this. And then we have subtracted from that, of course, or we will subtract from that in a second, the integral of v, which is negative e to the negative x, multiplied by du by dx, which is 1, all with respect to x. So you see how the integral here is much, much simpler. And of course we'll need some limits as well. Now, we can substitute in the limits as we go along, or we can do that at the end, it's up to you. But the second part of this just becomes the integral of e to the negative x dx with limits 0 and 4. So some people at this stage like to substitute the limits in, some people like to leave it all to the very end. It doesn't really make very much difference as long as you are careful with what you do. So this will integrate to give me negative e to the negative x between our limits of 0 and 4. And what I might do is actually combine these and then substitute in my limits of 0 and 4. So I get negative 4e to the negative 4 minus e to the negative 4. And then we're subtracting from that 0. And then minus 1. So be very careful. There's lots and lots of negatives involved in all of this. So you need to make sure you keep these clear. So this will simplify to give me minus 5e to the negative 4 plus 1. So we're going to have a look at two very special examples of integrals which require us to use integration by parts twice in order to complete the integral. So let's start off the process. I want u to equal x squared, which gives me du by dx equals 2x. And I want dv by dx to equal e to the x, which gives me v equals e to the x. So let's start off the process. The formula is up in the top right-hand corner. And let's do the integral. So the first part is uv, so x squared e to the x minus the integral of v, which is e to the x, multiplied by du by dx, which is 2x. Now, have a look at the result here. We can't then integrate this directly. We need to use integration by parts again. So the process then starts a second time. So you can pull the 2 outside the integral if you want to, but some people prefer to use that within the integration. So u equals 2x, giving us du by dx equals 2. And then dv by dx equals e to the x, so integrating that, v equals e to the x again. So we're ready to integrate by parts for a second time. Don't forget that this part of the integral has already been completed, so we must ensure we don't forget about this. It needs to be carried through to the rest of the integral. So x squared e to the x minus. Now, be very careful because there is a negative here, or subtraction here, and of course we've got another subtraction when we do the integral by parts again. So I'm going to put in a large pair of brackets here, Now, where are we up to in the formula? We are up to this part here, the new u multiplied by the new v, so that's this product over here. So that is 2x e to the x minus the integral of v. So just to confirm, we're at this part of the integral now, minus v, or the new v, multiplied by du by dx, so that's the product of these two parts here. So that's e to the x multiplied by 2, which can come out of the integral if we needed to, with respect to x. And now we've finally got a result that we can integrate very easily. So we end up with x squared e to the x minus 2x e to the x. Now note there's a minus here and a minus here, so this will become plus. And then, of course, when we do this integral here, we simply just get 2e to the x plus c. Let's take a look at another example, the integral of x squared sine x. So I'm going to choose u as x squared and dv by dx as sine x. So we'll start round 1 of integration by parts. dv by dx is sine x. Now this gives us v equals negative cos x, so immediately you need to be on your guard here because the fact that negative signs are involved will make all of this even more tricky at times, particularly because the integration by parts formula contains a negative. So first round of integration by parts, we have u multiplied by v, so that's x squared multiplied by negative cos x minus the integral of v, which is negative cos x multiplied by du by dx, which is 2x with respect to x. Now, the first thing I would do here is make sure we pull this part down into the next round, so negative x squared cos x. Now the next thing I would do is acknowledge the fact that there's a negative here, so we really want to write that straight away as plus the integral of 2x cos x dx. And then we want to start the process again. U is going to equal 2x, which gives us du by dx equals 2. And dv by dx is going to equal cos x, which gives us v equals sine x when we integrate. So we're ready for another set of steps. So we have negative x squared cos x. Now this time it's a plus, so it's a little bit less concerning than previously where we had a series of negative signs to contend with. Now we need to make sure we follow the integration by parts formula again. So just a reminder, we're doing this part first of all, which requires us to take the product of u and v. So that's 2x sine x minus the integral of v multiplied by du by dx. So that's 2, which can come outside of the integral sign, of course, sine x dx, and then let's finish this off. So we have negative x squared cos x. From this part here, we just have plus 2x sine x, but then here we're integrating sine x, which integrates to negative cos x, and there's a negative here that we need to think about as well. So this is going to become plus 2 cos x, and then of course there'll be a plus c at the end.